So in parallel with this testing program with the Robinson and John Wayne and Alameda, Los Alamitos, in parallel with that, I was maintaining a engineering program to get up to what I really felt was the mission I wanted, which was not the 20 minutes that the skeptics said I could do after being paid to prove me wrong, or the 1 hour, which was just my back of the envelope calculation. I felt the mission that I needed to do was 2 hours of flight time and 600 pounds of people and or cargo. So for me to be able to achieve my objective of 2 hours of flight time with the batteries and the motors and inverters that are out today, I had to improve the lift to drag ratio of that helicopter. Helicopters have almost all helicopters have a lift to drag ratio between 4 and 5. And those numbers don't probably mean anything, but by comparison, fixed wing aircraft, like that Gulfstream I showed you before, have a lift to drag ratio between 10 and 20. And so basically it says that, a fixed wing plane for an equivalent amount of power, an equivalent amount of fuel, an equivalent amount of payload that they're carrying is going to be able to travel 2 to 4 times as far as a helicopter. That's what those numbers can tell you. So we spent a lot of time evaluating different designs, and we came up with this canard design. So these front wings are called canards. Here you see a model of the plane from descent down to landing. So when the plane is in horizontal flight, the engines, the propellers, are providing forward thrust, and when we get ready to land, then the engines go ahead and rotate, and you have vertical thrust to come down flat. And this results in a lift to drag ratio of 20. So by both theory and practice, I'm entirely confident that by 2020, I'll be able to fly for over 2 hours with 600 people and payloads. Here you see highlighted the range for 2020, 463 kilometers. That's roughly speaking like 300 miles, 250 miles or so. The batteries are actually with that very good lift to drag ratio, and banking on every year the energy density efficiency of batteries has increased 8% a year. So if you just clock that 8% up through to 2020, we'll have the batteries down to 1,500 pounds or so, a little bit more than 1,500 pounds, about 2,000 pounds, so a third less battery weight actually. And then finally in the range equation, with a lift to drag ratio of 20, we're able to hit 600 pounds. I call this aircraft the GOPAT, grid charged, optionally piloted, which means autonomous capable, powered lift aircraft for transplantation. And you can see there that there's room for actually 2 pilots side by side, 3 organs being transported, which are easily accessible. The batteries go in the back here so that they help support this wing structure, and the batteries also go with the canard wing structure. Here's a close-up of the type of things we carry around in these electric helicopters. Hearts, lungs, livers. We keep all of these alive hours longer than were possible before. We also keep all of these organs at room temperature. Turned out that the results from transplantation are much better if instead of taking an organ out of somebody and putting them in an ice box where it's chilled all the way down, transporting it and then warming it up again and put it in the body, if you keep it at room temperature all the time, then the blood vessels don't all constrict and expand, and you don't get things like reperfusion injury. So those are what we'll be carrying in that helicopter. We've already partnered with the Mayo Clinic, one of the world's leaders in organ transplantation. So the Mayo Clinic in Jacksonville, Florida, Rochester, Minnesota, Scottsdale, Arizona are partners for moving these organs all around by the helicopters. DARPA has come to also partner us. DARPA has a vision called Organs on Demand. A soldier is hurt, damaged by enemy fire. Okay, bones, they can be set. A lot of things can be stabilized. How about their liver has been blown up? Are we going to put them on the liver wait list? Well, that's not going to work out very well. Instead, by us getting into manufacturing organs continuously, we can always have an organ available, even in a battlefield scenario, when one is needed. So our vision is moving forward with organs on demand. Today, we're using this procedure called EVLP that you saw those machines, and that's able to handle several thousand organs a year. We are also genetically modifying pigs so that the pigs produce human-friendly organs that function like ours and won't be rejected. And ultimately, next, we're moving into 3D printing of organs using a person's own cells so that nothing will be rejected in the body. The regenerated organ will look just like the same DNA of the individual. So when you add this up, when you're talking about not a few hundred organs, but hundreds of thousands or millions of organs, you are going to need a very large fleet of helicopters delivering all these. And so the fleet of GOPATs and the other electric helicopters we're developing will be able to autonomously distribute all of these organs.
3D bioprinters at United Therapeutics DECA Organ Manufacturing Center in Manchester, New Hampshire, print the inert collagen scaffold of a lung from its larger proximal vessels and bronchi to its millions of distal arterioles. End-stage organ disease patients give up a few cells in a biopsy, which will be transformed into inducible pluripotent stem cells, all matching the patient's DNA to avoid any need for immunosuppressants. It was just in the past decade that science has learned how to turn differentiated human cells back into stem cells. Thereafter, the newly made stem cells can be redifferentiated back into a wide variety of different types of cells. In our manufacturing laboratories, we will redifferentiate newly made stem cells from a patient into endothelial, epithelial, muscle, and connective tissue cells that match the patient's DNA. After expanding the numbers of these differentiated cells into the tens of billions needed to cellularize each organ, we stream them into the previously bioprinted scaffold. The entire process of cell expansion and recellularization via streaming takes about 2 to 3 months per organ. At the end of the process, there is a newly manufactured, personalized organ that matches the DNA of the intended patient. Once removed from its bioreactor, the organ needs to be transplanted within hours. A Transmedics cart will be loaded onto an E-Hang manufactured organ transport helicopter, or MOTH, for delivery to the surgeon's operating room.
I think a lot of us can have those electric helicopters in our garages too.